Hello everyone, and this is physics. In this video, I want to talk a little bit about resolving vectors into XY components. Actually, I really want to talk about part A, and that's to derive the equations which we're going to use in resolving vectors into their XY components. So this will be part A in order to derive the equations. In another video, I will actually use the equations and resolve vectors into their XY components. So this will be part A. To start part A, we're going to look at SOHCAHTOA. Let me write that down here. I'm sure you're already familiar with this. So this first part here is sine of some angle, we'll call it theta, is equal to the opposite divided by the hypotenuse. And here we have the cosine of some angle, we'll call it theta again, is equal to the adjacent divided by the hypotenuse. And this last one, that's the tangent of some angle. And we'll call that angle theta. Could we call it beta, gamma, doesn't matter, we'll call it theta. So tan theta is equal to the opposite divided by the adjacent. We're going to use this in order to derive the equations we're going to need in order to resolve vectors into their XY components. So going further, this applies to right angle triangles. So let me draw a right angle triangle here. And right angle means that one angle is 90 degrees. And these two angles, well, they can be anything less than 90. And we're just going to call this angle here, since I'm using terminology theta, I'm going to call this one theta. That one here really isn't important for this exercise. And a right angle triangle doesn't have to look like this. As long as it's right angles, it could look like this. And we'll call that theta. Again, this one here is not needed for our purposes. Or we can draw it again and make it look something like this. As long as one angle is 90 degrees, and we'll call this theta. And then SOHCAHTOA applies to all of these. This only applies to right angle triangles. I'm going to write that in blue. SOHCAHTOA only applies to right angle or 90 degrees. One angle has to be 90 degrees, so right angle triangles. Having said that, let's choose, I'm going to choose this triangle here because I have lots of room here to write on. And we'll start to derive the equations we need in order to resolve vectors into their two components, the x and the y. So consider a triangle. There's 90 degrees. And I'm going to call this angle right here theta. And that one here is not necessary for our purposes. The length that we have here, we'll call this length right here. Since that's theta, that length then becomes the opposite of the angle. So that length is the opposite. And this length here, since this is, we define this one as theta, this length here then is also called the adjacent length, that length and that length. And this length right here is also known as the hypotenuse. The hypotenuse. But I'm not going to use the word hypotenuse here. I'm just going to rename it. Hypotenuse is just the length from here to here. It has a special name, hypotenuse, because it belongs to a right angle triangle. But it just represents the length from here to here, or the magnitude. Another word for length, or the size of that length is magnitude. Magnitude. The magnitude of that length. And it starts with the letter m. So I'm going to call this m to represent magnitude rather than hypotenuse. Having done that, what I like to do is rename this adjacent length, that length, in terms of m and theta. We're not going to use any numbers here. We're just going to rearrange this using SOHCAHTOA. So in SOHCAHTOA we have the sine and cosine. Let's use cosine. I'm going to use this one. I just use a different color just to change it up a little bit. So cosine of this angle is equal to the adjacent divided by the hypotenuse. And as I said earlier, I want to relabel the hypotenuse with the letter m. So this is the same as saying the adjacent divided by m for magnitude, or the length of the hypotenuse. They're all one and the same. Rewriting this, just using that portion and this portion. Cos theta is equal to the adjacent divided by m, magnitude of the hypotenuse, m. What I'm really searching for is the length of the adjacent. So I just need to isolate the adjacent here. To do that, multiply both sides times m. Multiply this times m. The m's cancel out on that side and it comes over here to my left-hand side. This equation then becomes, and I'll go back to black, m cos theta is equal to the adjacent. What this really means is, another way of writing down adjacent is the length of the adjacent, the length of that side, is the magnitude of the hypotenuse, if I knew what it was, times the cosine of that angle, if I knew what it was. That would give me the length of the adjacent. In other words, I can rewrite this triangle using this equation, and I'll call this equation 1. If I rewrite that triangle, here it is here. I know this angle is theta. Some angle, I'm going to call it theta. I know the length of this hypotenuse, I'm going to call that m, so everything stays consistent. I know that this one here was the opposite. And now I know that the length of the adjacent, here's the adjacent, I can replace adjacent with this part. I can now define the length of the adjacent by using m cos theta in terms of the magnitude of the hypotenuse and the angle theta. If I knew what this number was and this number was, put it in that equation, that would give me the length of that side. Let's do the same for opposite now. And I'll do it over here. And to do opposite, we're going to use SOHCAHTOA yet again, except I'm going to use this portion, sine. And we'll go back to blue, just to change it up a little bit. So sine of some angle theta, here's my theta, and sine is the opposite divided by the hypotenuse. And that is also opposite divided by, I'm going to change the hypotenuse back to m like I did earlier. This changes to sine theta is equal to opposite divided by the magnitude of the hypotenuse, m. If I were to multiply both sides times m in order to isolate opposite, this equation then becomes m sine theta is equal to the opposite, and we'll call that equation 2. Now if I rewrite this triangle yet again, in terms of these equations 1 and equation 2, I've already done it here for equation 1, but just for clarity, I'll redraw it. So I can replace opposite with this term. And this is the basis for resolving vectors into xy components. Here's my right angle triangle. That's my sine theta. M is the magnitude of the hypotenuse. This will be the adjacent, but I'm going to call the adjacent m cosine theta. And now I can relabel the opposite as m sine theta. Effectively, what I've done here is put this length and that length in terms of the angle theta and the magnitude of the hypotenuse. Now, how is this related to vectors? Related to vectors. Well, let's have a look. Consider a vector. Now, a vector is typically drawn as an arrow, and it has a magnitude and a direction. So consider a vector starting here, and I was going in that direction, so I'm going to stay in that direction. Here's a vector, and this vector has a magnitude, has a size, and it's also at some angle. And angle 2, we're going to give it an arbitrary angle 2, an xy coordinate system. There's x, there's y. So it's, if you sweep upward from the x direction, we're going to call this angle theta. To resolve this vector into its x and y component, what we'll do is we need to project this down onto the x-axis. By doing that, we just simply draw a line which is parallel to the y-axis, and it touches the x-axis here. The length of this, or the magnitude of this vector here along the x-axis, in terms of what we had here earlier, here it is m cosine theta. And if I were to project this into the y-axis, go like so, I got a vector here now going up in the y-axis would be the y component. And the magnitude of the y component would be, well, m sine theta. So these are the two components. That will be the vector. These would be the x and y components. There's a little bit more to this, but for this video, I just wanted to derive these equations 1 and 2. I think this was equation 1. And I believe this one here was equation 2. In a follow-up video, I'll show you how to use these and with respect to vectors. But for now, these are how to derive these two equations, 1 and 2. And this is physics.